So we are starting to talk about something called matrices today, which I believe is brand new stuff for you guys, possibly not if you took Algebra 1 already. So we're going to start with the definition. There's a big wide space here. We're going to write a lot of things down about the definition of a matrix. So the definition itself, a matrix is a rectangular array of variables or constants variables or constants in rows and columns enclosed in brackets. All right, so that's the definition. So get that written down. So here's what typically happens. A matrix is named using an uppercase letter, so it might be matrix A or matrix B or whatever. So let me write you down a sample. So you'll typically see like capital letter equals, and then a big set of brackets, and then we just have rows and columns of numbers. So here's a sample that the book has. Okay, so we've got rows and columns, all in a big set of brackets. Notice there's no commas or anything. Everything's just kind of spaced apart so you know exactly where it's supposed to be. So let's talk about a few things here. Let's talk about first the dimensions. So you can write down the size of a matrix by writing its dimensions. So you would count the number of rows. So rows are counted this way. There are 1, 2, 3 rows. And then you count the columns this way. There are 1, 2, 3 columns. Oops, 3 columns. All right, and then when we write this, so m rows and n columns, when we write the dimensions, we write 3 by 3. First we write the number of rows, and then we write the number of columns. So this one in particular is a 3 by 3 matrix. I probably should have given you an example that wasn't a square matrix. That way you would have known which one was rows, which one was columns. But rows always goes first, then columns. So this is a 3 by 3 matrix. And then last thing, you can talk about each individual element. So each one of these values is called an element, and you name it based on its letter and based on its position. So like this one right here, the -1, for example. We give it a lowercase a, because it's in matrix A, and we call this element A21 because it's in row 2 and it's in column 1. So this is A21. And then like this one, for example, we would call this element A32 because it's in the 3rd row and it's in the 2nd column. So this is A32. So they all have names. A11, A12, A13, A21, A22, A33, A31, A32, A33. Of course, if our matrix was B, then we would start with B, etc. So that's kind of a quick rundown on matrices. Let's flip over. We've got a couple of examples here. Found my first mistake of this packet. It says the table displays U.S. Census data, and then there is no table. So here's the table that we are supposed to be looking at right here. So if we look at this table, we've got from 0 to 19, 20 to 39, 40 to 59. So I'm going to copy this column down, so just follow my lead here. So the table, we've got these ages. So the numbers down the left are ages, 0 to 19, 20 to 39, 40 to 59, and then 60 and up. This is age. And then there are males and females. So we've got 7.1, 6.8, 3.2, 1.1 for the male column, 6.6, 5.9, 2.2, and 1.4. All right, so here's our table. This represents Latino population in the U.S. in millions. All right, so again, Latino population in the U.S. in millions. So 7.1 million Latino males between ages 0 and 19, for example. So organize the data in a matrix. So by row, we've got these ages. We don't include this in our matrix, we just include these values in our matrix. So the matrix that we're going to set up would look like this. Down each column, so the first column would represent the males. The second column would represent the females. And then if we're looking by rows, the first row represents age 0 to 19, the second row represents age 20 to 39, the third row represents age 40 to 59, and the last row represents age 60 and up. So this is all we're looking for when we want to organize the data in a matrix. It looks just like this. Add the elements in the columns and interpret the results. So if we add this first column, so column 1, let's add all these things together, and of course, no harm in using a calculator here. So add 7.1 plus 6.8 plus 3.2 plus 1.1. And then while we're at it, while we've got the calculator out, let's add the second column as well. 6.6 plus 5.9 plus 2.2 plus 1.4. That gives me 16.1. So for my first column, I got 18.2. And what this represents is how many total, because I added all of the men together, this column right here, and so that represents total male Latino population. In the U.S. And then column 2, let's sneak this in here. Column 2, when I added those together, I got 16.1. And so that would be 16.1, and that is the total female Latino population in the United States. All right, so that's the interpretation of adding the columns together. Adding the rows together, we could add this row, we could add this row, this row, this row. And so if we add the first row, we get 7.1 plus 6.6. Oops, that was times. Plus. So the first row, we get 13.7. Second row, 6.8 plus 5.9. In the second row, we get 12.7. Third row is 3.2 plus 2.2. It's 5.4. And in the last row, 1.1 plus 1.4. So what we just did is we added the men and women together in each age group. So this first row was the total number between 0 and 19. And then, for example, the last row was the total number from 60 on up. So if we write down these values, so row 1 ended up being 13.7 when I add these two values together. Row 2 ended up being 12.7 when I add these two values together. Row 3, add these two together, I get 5.4. And finally, row 4, add these two together, and I get 2.5. Okay, so what these are, this is the total, let's say, Latino population in each age group. So like 5.4, for example. It says there are 5.4 million Latinos in the United States between 40 and 59 years. Right? And then last, would finding the average of the rows or columns provide any meaningful data? So would finding the average number of men in each age group? Probably not. I don't know if an average would really do anything, or finding the average between men and women in this age group, probably not. Doesn't really seem like we're going to get any meaningful data out of that. So probably not. I don't really know what that would give us. The totals give us something meaningful, but I don't see the averages really doing anything for us. All right, so adding and subtracting matrices. We're going to look at some algebraic operations. We can add and subtract matrices, and then we can multiply them by a constant. So adding and subtract, first of all, basically for adding and subtracting, you just add or subtract each corresponding element. So you just add or subtract each corresponding element. If and only if the matrices have the same dimension. If it only works if the matrices have the same dimension. All right, so get that definition down. We got 3 things to try right here. Add or subtract the matrices. So again, we want to see if the elements have the same matrices or have the same dimensions first. So if we look at this one has 2 rows, 2 columns. So this one is a 2 by 2 matrix. This one has 2 rows, 2 columns. So this one is a 2 by 2 matrix. So that fits our condition right here. The matrices do have the same dimension. So when we add or subtract the corresponding elements, to see if they're corresponding, that means they're in the exact same position in the matrix. Same row, same column. So like these two, for example, the -3 and the -4, those are in the same position, and so those are the ones that I subtract. So since each one of these matrices was 2 by 2, the new matrix I get is also going to be 2 by 2. So I do -3 minus -4, which minus a negative turns into plus. So -3 plus 4, I end up with a 1 when I subtract those two values. Then move over here to the 4 minus 12. 4 minus 12 gives me a -8. -9 minus 8, they're both negative, so my result is even more negative, -17. And then -5 minus -7, so -5 plus 7, and I get a +2. And that's it. Literally all I'm doing is just subtracting the corresponding elements in each matrix. So let's try part B. Here I've got 2 rows and 3 columns, so that is a 2 by 3 matrix. Here I've got 2 rows and 3 columns, so that is a 2 by 3 matrix. So because they're the exact same dimensions, they're the same size, that means I can add them together. So my new matrix is also going to be 2 by 3. So let's go across the rows, and this time I'm adding each corresponding element. So add a -9 to a -4, and I get a -13. Move over 1 element. I'm adding a +8 to a -3, and that gives me +5. Then I'm adding 3 plus 6, which of course is 9. Second row, -2 plus a -9 gives me a -11. +4 plus a -5 gives me a -1. -7 plus a +18 gives me a +11. And then I close off my matrix. So again, that's it. Nothing else to do beyond there. As long as you can count the dimensions and then add or subtract, which of course you could even do with a calculator if you're not sure of your addition or subtraction skills. Last one here. I've got 1, 2, 3 rows and 2 columns. So this is a 3 by 2 matrix. Here I've got 1, 2 rows and 4 columns. So this is a 2 by 4 matrix. This one, they don't have the exact same dimension, and so therefore, like, I wouldn't even know how to add or subtract them. Like, maybe I'd try to add the 8 and the 5, or subtract then the -3 and the 1, but then I run out of elements here. If they don't match perfectly, then I can't figure out what the corresponding elements are, so I couldn't possibly add or subtract them. They don't even have the same number of elements. This one has 6 elements, this one has 8 elements. Even if they were in the right spots, we'd have extra elements here. So this one, you can't. It's completely impossible to subtract these. Okay, now multiplying by a scalar, our second operation here. So multiplying by a scalar is just a constant, just so we know. Scalar is just a constant, just a number. So we're not multiplying by a variable, just a number. So what you're doing for matrix multiplication by a scalar is you are going to multiply each element by that scalar. So the word scalar sounds like scale. I'm sure you've heard of things with like a scale model or something like that before. So when you scale a matrix, you either scale it up or you scale it down, whatever. So we look at this one right here. We've got our first example of multiplying by a scalar. So it says if t equals, and then it gives us this matrix, then it says find -4 times t. So if we want to take -4, basically taking that -4, it's almost like distributing. So we're going to multiply every single element by -4. So again, it's just basic multiplication. So -4 times t equals, so I set up my matrix. This one is a 2 by 4. I'm going to multiply every single one of these elements by -4. So it gets scaled by a factor of -4. That's why we call it a scalar. So -4 times 8 gives me a -32. Move to the next element. -4 times 0 is just 0. No matter what I multiply by 0, I end up with a 0. -4 times 3 is a -12. -4 times -2 comes out as a +8. Don't forget, negative times negative is a positive. Down to the second row, -4 times -1 is a +4. -4 times a -4 is a +16. -4 times a -2, again, is a +8. And -4 times +9 gives me a -36. And that's it. So this matrix right here is a multiple of this matrix right here. I multiplied every single thing in it by a -4 to get my new matrix. All right, properties. For any matrices A, B, and C, for which the sum and product are defined, the following properties are true. So we talked about all these properties that we have for real numbers. Matrices are this entirely new category of math. And so we don't really know necessarily, does the commutative property work? Does the associative property work? So we've got these properties so we can lay this down for us. So the commutative property of addition. This says that capital A plus capital B is equal to capital B plus capital A. So remember, those capital letters represent matrices. Now it's very important, it says right here, if the matrix sum is defined, that means that A and B must be the same dimension. Because if I can add or subtract them, they must be the same dimension. So when I add them, A plus B is the same as adding B plus A. It's not the same with subtraction. A minus B is not the same as B minus A. That's why we're only talking about addition here. The associative property, if you remember this from the first chapter, the associative property is what kind of groups things together. So if you add A and B together first and then add C, you'll get the exact same result as if you add B and C together first and then add it to A. So that's the associative property. We have a left scalar distributive property as well as a right scalar distributive property. So if you have a scalar on the left, outside of the sum A plus B, rather than adding A plus B first, you could distribute the scalar first. So you could multiply the scalar times A and then plus multiply the scalar times B. So the distributive property works the same as it does with normal numbers as well. And then right scalar distributive, it's possible technically, and this is going to sound strange, but it's technically possible to put the K on the right. When we get to multiplication in the next section, multiplying on the left is actually sometimes different than multiplying on the right when you're dealing with matrices, and like I said, we'll get there in the next section. But here we're kind of distributing the A times the K, so we get a KA, and then plus distribute the B times the K, so we get a KB. It doesn't look like these two things are different, and of course from what we know about matrices right now, they aren't. But like I said, when we're dealing with matrix multiplication, multiplying on the left can sometimes be different than multiplying on the right, and that will make more sense when we get there in the next lesson. Okay, example 4, lots of combinations here. So what we're going to do, we want to find -6b plus 7a. Think order of operations. The very first thing that we need to do is find what this is. We need to do the multiplication first, and then find what this is. So let's do some side work for that. So -6 times b equals, so I'm going to take this matrix right here, multiply everything in it by a -6. Okay, so 12 times -6 gives me a -72. 5 times -6 gives me a -30. Again, 5 times -6 gives me a -30. -6 times -4 is a +24. -6 times +4 is a -24. -6 times -7 is a +42. And then 7 times a. Let's write that down as well. So 7 times a. Now here's my matrix A. I'm going to multiply everything in here by a 7. So again, just multiply every single one of these elements by 7, and it gives me a brand new matrix. So -5 times 7 is -35. 3 times 7 is 21. 6 times 7 is 42. -8 times 7 is -56. 2 times 7 is 14. 9 times 7 is 63. There's my second matrix. So I did the multiplication part first. I figured out what -6b is. I figured out what 7a is. Now my last thing is to add them together. So since they are the exact same dimension, they are both 3 by 2 matrices, I just add them together just like I was doing on the front, add each corresponding element together, so plus, so starting with the negative 72 and the negative 35, I add those together, combine them up, I get a negative 107. A negative 30 plus a positive 21 gives me a negative 9. A negative 30 plus a positive 42 gives me 12. Positive 24 and a negative 56 gives me a negative 32. Negative 24 and a positive 14 gives me a negative 10. And a positive 42 and a positive 63 gives me a positive 105. So that new matrix is my final answer right here. Okay, last example. Use the data to calculate the average yearly sales and wages for the company, assuming 260 working days. So we've got a lot going on here. We have all of these values. We've got Miami, it looks like a Miami office, maybe a Tampa office, a Tallahassee office. So if we're trying to figure out the average yearly sales and wages for the company, the average, what we would do is add, so if we're looking at what, sales and wages, entry, assistant, associate, okay, sales and wages, we're going to add them all together, and then it says assuming 260 working days. So if we add everything together, entry, assistant, associate, all of these values are going to end up getting added together, and then we're going to try to average them out. And so the 260 working days, kind of keeping that in the back of our mind, that one, we cannot forget about all 3 of these different levels and all 3 of the offices. So I think what we're going to do is just add these together and average everything out. So adding these, and then we've got kind of 9 different categories, I guess. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're going to add together and then divide by 9. So these things, or you know what we could do, is actually add the matrices together. Yep, that's what we're going to do. And then divide. So all of these things, we are going to add the Miami matrix plus the Tampa matrix plus the Tallahassee matrix. So add them all together. So we've got some big numbers to deal with. So first we've got 900 plus 900 plus 1050. So that is 2850. And then move over to this next one, 145,000 plus 122,000 plus 109,500. Okay, then down to the next row, 2,400 plus 1,800 plus 1,800. So this spot gives me 6,000. Then add these 3 together. So 225,000 plus 145,500 plus 135,000. That gives me 505,500. And then onto my bottom row. So 2,700, bottom left, plus 1,800 plus 1,800. 6,300. And then these 3 right here. So 290,000 plus 160,000 plus 150,500. Okay, so here is my brand new matrix. So this is what I got from adding everything together. So we're trying to calculate the average yearly sales and wages. So these are yearly sales and wages. So if we combine everything up here, assuming 260 working days, so we are going to take this and then divide it by 3, since we just added these 3 together. So really what we're going to do, instead of dividing by 3, we're going to multiply by 1/3. So every single one of these values is going to get multiplied by 1/3, and then that'll be our final answer. It'll give us all the averages. So 2850 times 1/3, actually let's just do divided by 3 because that's the same thing. That gives us 950. And then if we move right here, so 376,500 divided by 3, that gives us 125,500. And then 6,000, hopefully we can do that, divided by 3 gives us 2,000. The 505,500 divided by 3 gives us 168,500. And then the bottom row, 6,300 divided by 3 2,100 in my last value, 600,500 divided by 3. Oops, I need to get a fraction for that apparently. Okay, so this is 200,000, 166, and then I guess 67 cents. All right, so these are all of the average yearly sales and wages for the company. So when I average the Miami company with the Tampa company with the Tallahassee company, this is the average wages for an entry position, average sales, average entry for an assistant position, average sales, average entry or average wages for an associate position, average sales. So that would be our final answer. All right, I believe, yep, we are all set.